I wanted to do a quick little, I wanted to do a video, but this is the easiest thing I can figure out how to do to describe the PTS system for those of you that need to go over it multiple times. I've done a small drawing using just a word drawing pad, and I'm going to discuss the three ways that the PTS system can help bacteria make a molecular choice between different substrates. There's inducer exclusion, that excludes non-preferred substrates from even getting into the cytoplasm. Inducer expulsion spits out the non-preferred substrate, where the third, catabolite repression, is going to control adenylate cyclase in the cell membrane. Adenylate cyclase, if you remember, converts ATP to cyclic AMP. And the cyclic AMP is needed to turn on non-preferred genes. Alright, let's start. Phosphoenol pyruvate is a high energy molecule. It's the next to last step of glycolysis, if you remember. And PEP, or phosphoenol pyruvate, has the ability to give off that phosphate group. It can be used to make ATP like it is in glycolysis, or it can be used in this electron transport chain. If it gives its phosphate group to the enzyme 1, thus phosphorylated the enzyme 1 molecule, then that phosphate group can be transferred from enzyme 1 to the second protein in this chain, which is called HPR. So they're playing hot potato with the phosphate group. Phosphate moves from enzyme 1 to HPR, and from HPR to enzyme 2A. In class, I called it enzyme 2A glucose. And as it phosphorylates down that chain, it can saturate all of the enzyme 2A into the phosphorylated form if there's no glucose coming into the cell. Now at the top there's a little gray circle that's the preferred substrate transport protein for glucose. If glucose is present outside of the cytoplasm of the cell, it will come through that transporter into the cell, and it will dephosphorylate the enzyme 2A molecule faster than the transport chain can transport phosphate groups down the chain, which is going to result in an altered ratio of the phosphorylated to the dephosphorylated forms of the enzyme 2A. A dephosphorylated enzyme 2A molecule is going to have the ability to bind to the non-preferred substrate transport protein for stuff like fructose or maltose, whatever the non-preferred substrate is. And it blocks it from being able to transport that non-preferred substrate even into the cytoplasm. So it's an inducer exclusion. It excludes the inducer from getting into the cytoplasm. The inducer itself is the sugar that would turn on genes for the degradation of the non-preferred substrate. So if it were maltose coming in, it would turn on a maltose gene because it's an inducer for a maltose gene. It doesn't fully turn on unless it has adenylate cyclase converting ATP into cyclic AMP. So in the presence of lots of glucose, you've dephosphorylated more of the enzyme 2A. That lets the cell know that a preferred substrate is present in the environment, and the enzyme 2A in its dephosphorylated form can bind to the non-preferred substrate transport protein. The inducer expulsion is a little different. If you have a non-preferred substrate like fructose, fructose would be in the cell, and then when a preferred substrate like glucose becomes available, then what would happen is the HPR would dephosphorylate the non-preferred substrate, thus giving the phosphate high energy bond back down the chain to the enzyme 2A, providing energy to lock glucose into the cell and also dephosphorylating the fructose so it can flow out of the cell and not take up a space that a preferred substrate could hold. Now, third and certainly not least is catabolite repression. That goes back to the adenylate cyclase. The dephosphorylated form of the enzyme 2A means there's plenty of glucose available. So the dephosphorylated enzyme 2A will have a negative effect on adenylate cyclase, thus reducing the amount of cyclic AMP in the cytoplasm and shutting down or preventing genes from being turned on too much for non-preferred substrates. If there's not much glucose coming into the cell, the opposite is true. The enzyme 2A in the phosphorylated form has a positive effect on adenylate cyclase and speeds up its activity. So that's it in a quick nutshell, and I'll post this and I hope it helps you. Thank you.